melt is some mixture of ringwoodite and perovskite that depends on what the volume of the melt is. And we ignored actually 5-coordinated silicon, but it turns out that when you calculate the isotopic properties of 5-coordinated silicon, it's exactly in between 4-coordinated and 6-coordinated silicon. So you can treat it as a 2n member problem, at least at this level. Okay, so we're essentially taking this model and parameterizing it as a mixture of ringwoodite and perovskite, so we get a variation something like this, or something like this in the coordinations as a function of the specific volume of the melt as a function of pressure and temperature. And here's the more sophisticated model showing the mixing end members. So down here at high temperature and low pressure, you get essentially all 4-coordinated silicon, like ringwoodite. Up at high pressure, you get essentially all perovskite, like melt, and in between there's a transition. But the transition is actually very boring in terms of its pressure behavior. What you see is that there's almost an exact counterbalance between the tendency of phonon frequencies and zero-point energy effects to get bigger as you compress a structure, and the coordination to increase as the pressure increases, which tends to reduce zero-point energy effects. And so we can actually slap some perspective mantle liquid eye on top of this to get a sense of what might actually happen in a differentiating Earth. And what we see is, even at sort of tens of GPAs of pressure, we're still seeing this kind of half a per mil, perhaps, effect of segregation of light isotopes of silicon into metal droplets that may eventually form a core, but it's potentially sensitive to the temperature at which the core segregation is occurring. It's not independently dependent on the pressure. Okay, so actually that simplifies things. If we can actually figure out what's going on in the system in the Earth as a planetary system, we actually don't have to worry about possible accidental degeneracy between pressure effects and temperature effects. Okay, so this is the silicon story. There's a lot of work to be done. In particular, I have to figure out how to actually write up what I'm doing here in such a way that it's not so simplistic, it's kind of absurd. But I just want to point out that, as I mentioned at the beginning, there's been this great technological leap in our ability to measure isotope compositions of things. And it's literally the case that every 2 months in the geochemistry literature, there's some new isotope system that somebody figures out how to measure at high precision. And essentially every 6 months, somebody's saying something about whether planets are different or the same in terms of the isotopic composition of element X. So this is a field that's it's burgeoning without necessarily having a purpose yet. And so just to show for an example, hydrogen isotope partitioning between metal and various other phases, where you can get some really huge isotopic partitioning effects. This is not in per mil. This is just essentially the equilibrium constant for exchange of deuterium and hydrogen between metal and things like H2 or water vapor or a silicate melt. And this is going to be true for iron. It appears that likely that there are large segregation effects for hydrogen, carbon, nitrogen, oxygen, and sulfur, although it's not so clear if we can actually detect these because some of these are volatile elements. We don't actually know what planetary budgets are like for them. But of potential interest in particular are what's going on to these things at high pressure. It's probably happenstance that silicon has the simple behavior it does. Other elements, there's no particular reason to for them to behave in such a simple way. And non-ferrous transition elements, I mean, the way we try to figure out how the core formed is by looking at partitioning of things like platinum group elements or vanadium or chromium. And many of these elements have isotopes that may potentially be separated when you segregate metal from a silicate. And they're all going to be looked at by somebody. So it's up to us to try to understand them. OK, so I'm essentially done with the science. I just want to, since this seems to be an important place to mention it, the little part I talked about on high pressure stuff, we've almost exclusively done with quantum espresso, but we actually use all kinds of stuff depending on what kind of problem we're interested in. Periodic boundary condition codes, molecular codes, relativistic codes, molecular dynamics, empirical force field codes. Our hardware usage, actually, this is kind of a theme. We aren't actually at the cutting edge in any sense. Many of the important calculations we do are like 2 cores over a few days or something like that. And I have a small cluster of my own group's use. We also have access to a general purpose cluster at UCLA, which is actually oversubscribed. And so I don't use it very much simply because it drives me nuts to wait hours or a day for something to go through queue. And our computations tend to be small but long, particularly phonon calculations don't seem to parallelize that well. And for more complicated structures, we have to run for like a week or two. And most supercomputing systems tend to be set up, as far as I can tell, to run like a 12-hour job on 1,000 nodes or something like that. And you really have to explain to them what you're doing for them to let you run something for a week. They don't like that, and you have to sort of make your case. So our main near-term resource, we're doing okay. We can do the calculations we want to do. But using like shared resources, the main thing is we want to be able to get on it, try something, know if it's working right away, and be able to go back and tweak it. And so not so many processors is the issue, but being able to get them when we need them, particularly when you're teaching most of the time, and so you have to spend an afternoon in a week doing something. And we need it stable so we can run a month at a time. And in terms of a wish list, it would be nice, since people are working through measurements of various elements, some of them obscure, some of them commonly studied. It'd be nice to have software that can treat these different elements in a fairly self-consistent way, because we're comparing different types of substances with different types of bonding environments, but we want to get this vibrational component of the energy the same for a metal as we do for a silicate, for instance, or the same for an insulator as for some other kind of material. And that includes dealing with other types of bonding, things like iron oxide, for instance, doing phonon calculations over more processors efficiently. And the last thing I'll mention, not having come from any kind of computational chemistry or any chemistry background at all, I sort of taught myself how to do this stuff as I went along, but I don't actually really know what I'm doing. I kind of know what I can do to make something work. And when it comes to train students to do stuff similar to what I'm doing, it's a little bit of a black hole. I'm not even sure where to start. And the chemistry departments don't really teach this stuff in a formalized way. And the physics departments don't really teach the stuff in a formalized way. So I try to teach these seminar classes that get students, even if they're not going to do this stuff as their main research, a student who's doing mass spectrometer technique development, or a student who's going to be doing diamond anvil cell work, it'd be helpful if they had an idea of what atomistic reasoning is about and what kinds of things you can make calculations of. They can design their experiments. They can think of problems with those ideas in mind. And right now, it's kind of difficult to actually figure out how to get them to that stage where they're like aware and literate in these techniques, even if they're not using them at sort of the cutting edge level. Thanks.
Yes. I guess I have a science question, which is your equilibrium assumption looks a lot like you're basically putting the planet on the silicon SiO2 buffer. That seems to be embedded in this. That's effectively what an Mg2SiO4 Fe3Si equilibrium looks like. It's look a lot like
it's close to iron wüstite.
Are you sure it's close to iron wüstite?
It is close to iron. Yeah. So Ed Young and other people have done this in some detail, and it's so at low pressure, instantite chondrites get you there, and they're like iron wüstite minus a couple log units or something like that.
The couple log units matter.
But it's iron wüstite minus 1, iron wüstite, something like that.
It's sub-iron wüstite, and that's important.
I think, and
below iron wüstite.
one of the ideas of this is that if this is really what's driving this isotope effect that we see, that's consistent with the idea that there's sort of a reducing core of the Earth, or the Earth started out in a more reducing state than it presently finds itself in, at least from our perspective on the surface.
To get the mantle a little more oxidized out of that as well, because you start with iron wüstite.
That's one of the broader implications. Although you should, I can't do this justice, but in fact, if you look closely at the thermodynamics, apparently it's actually not that, because of the impurities in these systems, it's not actually as far from what we think the core, the mantle is as we thought.
And let me follow up quickly. You basically did an equilibrium calculation. That's because you can, as opposed to the kinetic isotope effects, which may have been important in the nebular vapor. And there have been
absolutely.
There's a huge literature on kinetic isotope effects.
There's a
Can
huge.
You just talk for a few sentences about the underpinning assumption of equilibrium isotope fractionation versus kinetic isotope?
So there's a large literature, particularly in cosmochemistry, on condensation effects and condensation effects and their effects on isotope fractionation. There's mechanistic ideas for how those processes occur, but they are still at the stage where they contain important fudge factors. So you can't sit down to first principles, and that would be actually incorporating dynamics, right? Actually looking at transport processes and bond breaking. That would be an important advance to make.
Quick one. Pretty quick. Just an idea to throw in the audience. You mentioned the pedagogical component, which is missing actually in our community generally. I'm sure Renata teaches first principle calculations. I teach them to a large extent too. Maybe we can organize some network of universities where you could send students to Renata and me, or perhaps Boris maybe teaches some of these calculations.
That would be interesting. I would be happy, frankly, for even just like a very simple curriculum, like, you know, some homework ideas, or, you know, where do you go in the literature to find the basic paper on
I'm not
X?
sure how to organize this